We made a prediction that switch C was going to be the root for all of our VLANs in this topology based on switch C's MAC address if the priorities were the same. Let's verify that. Let's go to switch C, and here's a command we can use for verification and troubleshooting. It's show spanning -tree, and if we just pressed enter right now, we would see the spanning tree instances for each VLAN. If we want to look at them individually though, I can just say VLAN and give an identifier. I'll say show spanning tree VLAN 100, and we can see that this bridge is the root. It tells us very clearly. It tells us the bridge address for this bridge for this switch, and you'll notice it matches the MAC address for the root. And as a result, we are the root. You'll see that the priority is at the default of 32.768, but notice that the bridge priority and the root ID priority, it's a slightly different number. What's going on here? Well, this is something that happens with PVST Plus. Specifically, PVST Plus says that the bridge ID field inside of our BPDU, the bridge ID field has to carry VLAN ID information. So what PVST Plus does, it uses 12 bits inside of the bridge ID to indicate the VLAN. In this case, notice the extended system ID is 100. Well, that's the number of the VLAN. We're looking at the spanning tree instance for VLAN 100, so that is the extended system ID, and that results in a bridge priority of 32.868. It's 100 greater than this default priority. The way we get this number is we simply add the priority of the bridge to the extended system ID, which is the VLAN. Let me show you with VLAN 200. If we change to 200, you'll notice that now the extended system ID is 200 and the resulting priority is 32.968. We're still the root. It's just that the priority that we see here, it's a combination of this priority and the extended system ID. But we see we are the root for VLAN 200. Just for completion's sake, let's take a look at VLAN 300. And no surprise, we're the root for VLAN 300 as well. And in our topology, when we were doing this on paper, we predicted that all of the ports on the root bridge would be designated ports. And we don't need to take the time to look at this for VLANs 100, 200, and 300 because it's going to be the same at this point. Even though they're each running their own instance of spanning tree protocol, they're the same. The root bridge and all of the port roles for all of the VLANs, they're the same right now. Let's verify this. Do we really have designated ports on every port on switch C? Let's take a look. Here's the role. And for all of these trunk ports, look at this. Everyone is designated. Oh, we can also see that this link, gigabit 0/7, that goes over this 100 meg link, you can see the port cost is 19. That's the cost for 100 meg Ethernet, and we have a cost of 4 for these gig links going up to switch A. No surprise there. Let's make sure that switch A is behaving as expected. Let's do a show spanning-tree VLAN 100, and it would be the same for VLANs 200 and 300, of course. And we can see who is the root bridge. It's not us, it's this MAC address, which is the MAC address on switch C. The cost for us to get to the root, it's a cost of 4. We can see that our root port, which has a cost of 4, is interface gigabit 1/0/13. That's what we predicted because that was a lower port number than gigabit 1/0/14. We predicted that that port would be blocking, and sure enough, look at this, BLK. We are blocking on that port. We also predicted that for the link going between switches A and B, that the switch A port would be the designated port for that segment, gigabit 1/0/15, and sure enough, it is the designated port for that segment. Let's go to switch B, and let's do a show spanning tree VLAN 100. We predicted that fast Ethernet 1/0/1 would be blocking, and it is. And we predicted that fast Ethernet 1/0/2 would be the root port for this bridge, and it is. We've now confirmed that our calculations match up with a real-world implementation. And let's say that in the real world, we wanted to influence this a little bit. We wanted switch A to be the primary root bridge for VLANs 100 and 300, and it could be the secondary root bridge, in case the primary failed, for VLAN 200. Switch B is just the opposite. We want switch B to be the secondary root bridge for VLANs 100 and 300, but we want switch B to be the primary root bridge for VLAN 200. How do we do that? Very simple. We can go to switch A, and notice before we do anything, if I do a show spanning tree VLAN 100, notice that our priority right here is 32.768. We're about to give a command that can change that. Even though we could set this to a value of our choosing, it's often easier to give the following command. We could go into global configuration mode, and I'm going to say spanning -tree VLAN 100, and I'm going to say root. Let's give some context sensitive help. I could say primary, or I could say secondary. I want this switch to be the primary root bridge for VLAN 100, so I'm going to say primary. I also want this switch to be the primary root bridge for VLAN 300. So let's set that. And for VLAN 200, I want it to be the secondary. Let's set that. We'll say secondary. And based on that, let's see what the bridge priorities are now for those different VLANs. Let's do a show spanning -tree VLAN 100. And it says this bridge is the root. Fantastic. And we see that the priority that used to be 32.768, it's now 24.576. I bet we'll have a similar result for VLAN 300. And we do. The priority 24.576. That's the same as we had up for VLAN 100. What about VLAN 200 though? We said we wanted this to be the secondary root bridge for VLAN 200. I wonder what our priority is set to now. Well, it's not quite as low as it, but it's lower than the default. It's 28.672. Let's set this up on switch B. Let's go to switch B, and in global configuration mode, we'll say spanning -tree VLAN 100 root secondary. We also want to be the secondary root for VLAN 300, but we want to be the primary root for VLAN 200. Let's update that. And we're done. Let's verify it. Let's do a show spanning -tree for VLAN 100. We're not the root. We're not supposed to be the root, but we do have a lower bridge priority than switch C. So for VLAN 100, we've got a priority of 28.672, but for VLAN 200, we are the root. None of our ports are blocking for VLAN 200. We're designated ports all the way around because every port on a root bridge we said would be a designated port, and that's the case here. What about for VLAN 300? This should be identical to VLAN 100. Yeah, we're not the root, but we do have a priority of 28.672. And let's make sure that on switch A we really are the root for VLANs 100 and 300. Let's do a show spanning -tree VLAN 100. It says this bridge is the root. Fantastic. And we'll make sure that we're also the root for VLAN 300. And we are. What we've done in this discussion is, on paper, we predicted who the root bridge would be in a topology, who the root ports would be, who the designated ports would be, who the blocking ports would be, if we just connected all the switches together with their default settings, and that proved true when we gave the verification command on each of our switches. And then, from a design perspective, we said we really want switch A to be the primary root bridge for VLANs 100 and 300, and we configured that. And we wanted it to be the secondary root bridge for VLAN 200, and it was sort of the opposite for switch B. We wanted switch B to be the primary root bridge for VLAN 200, and the secondary root bridge for VLANs 100 and 300. We made those changes and verified the results.